Good afternoon. So today we have to carry on from where we left off in the last class in our derivation of the reduced model for Taylor dispersion. But that also gives us the break, natural break between these classes gives us a chance to just review what we've been doing. Okay. So remember, after scaling the model, we ended up with a system that looked as follows. So we have a linear operator L acting on C, right? And the operator was just diffusion in cylindrical coordinates. Right? And this was equal to Peclet right? I've just written it a slightly different way, but so this Peclet comes in front of the time derivative if we view things on long time scales. Right? And we saw how if we choose the short time scale, this Peclet will go off. It will be 1. So therefore, when we take the limit of Peclet going to 0, we'll see that we have dc by dt is equal to LC. And then the question to ask is whether L is singular, that means whether it has a null space, and we'll find that it does, and therefore it will admit a center manifold reduction. The alternative way is to retain P here, and then when you take the limit, right, you will see that you have LC equal to 0 with a null space, right, which means that the leading order solution cannot be determined. You're at a singular point, right, and you need to then do this Lyapunov-Schmidt reduction. So both things are the same as we saw. So then we proceeded with it, right. The first important thing we recognized was that this operator L is self-adjoint, which we will come to at the end of this lecture. Right, so we saw basically L is equal to L star, which that is. So for two functions u and v, okay, if I do the inner product, that means I act L on u and take the inner product with v. Right, in general, I can switch the operator to the other side, okay, and the corresponding operator I get will be L star, and usually it's different from L, except for the special case when it's symmetric or self-adjoint. If I was to discretize this problem in R, it would become a matrix. L would be a matrix, right, the finite difference matrix, and you will see that the matrix would be symmetric. Same thing. Fine, so we'll come back to how we can check whether this is true, and when it is not true, how one would get L star, which will be important later when we go to stochastic processes. For now, let us take it as a given and proceed. So when we know this, the important thing is that why this is important is because the key step, there are two key steps, right, in the procedure. The first is to write C as a decomposition, right? So we did step 1, right, which was to decompose, right, C, right, into a part that belongs to the kernel of L and the complement, right? So that is a null space of L. So L we have anyway, we can find its null space by solving LC equal to 0. And we did that and saw that C equal to constant is in the null space. That means null space is one-dimensional, spanned by just 1. Okay. So that is fine. So in fact, when we did that, we saw we could write it as when you project it onto 1, it's like taking the integration with respect to 1, which is basically the cross-section average, right, if I multiply by 2. So I can write C as its cross-section average times the null space vector, which is just 1, so I omit it here, plus the deviation, right? And this deviation, ultimately I will find, the whole point is that because I'm looking at long time scales, its dependence on x and time is only through C bar, which depends only on x and time, right? This of course will have some R dependence, right? And it depends on the C bar, and therefore it depends on x and time only through C bar. And the important thing is that its average of course is 0, and the C tilde will also satisfy the same boundary conditions as our original problem, right, which was no flux. Right? At the center line, it's symmetric. At the walls, you have no flux. Okay. So those same boundary conditions, of course, will carry on to C tilde. Right? But in addition, you have this condition that its average must be 0. We'll see where one has to use it. Okay. So that is the decomposition. And the second step, right, is to project my original equation into two parts also, right? So, but now I have to project, of course, in the range space, so in the codomain, right? This kernel is valid only on this kind of decomposition has to do with the functions that the operator acts on. And then it gives you a function which is in the codomain. So that because this operator has a null space, it will also have a limited range. It won't cover the whole available space, right? So when I decompose, I have to decompose the original equation into the range and the range complement. Okay? And the range complement will have the dimension of this kernel. Now to do this projection, I need to know a basis for the range complement. Right? Just as I needed a basis for the null space of L, I now need a basis for the range complement of L. But to find this is difficult. Right? But so this is where this what's called the Fredholm alternative is useful. It tells me that the range complement of L is the same as the null space of L star. Okay, so to actually project onto the range complement, I first need to find L star C equal to 0, find the null space of L star. But in this case, L star is equal to L. So I know that the range complement is spanned again by just 1. So when I project it onto the range complement, it's again like taking the cross-section average. But that's only because L is equal to L star. If L star was different, I would have some different function other than 1 to span the range complement. I'd have to project with respect to that. Okay, so that is, we'll see that when we go back to stochastic processes. So for now, I have the self-adjoint character. So we had also done this in the last class, right? Project the equation onto the range complement, right, of L and the range of L. Okay. So the range complement equation will give us a reduced model because it has only one dimension, right? And the range complement part of the equation will give an equation for C tilde. So we had done the first part, correct? We had projected our equation. So I had done this, right? I had taken LC. Yeah. Okay. And what happens is this thing goes off. We saw it by the calculation, but it also has to go off, right? Because I'm projecting the action of LC into the complement of the range. But by definition, whatever this vector is will lie in the range. Right? So it will have no part in the complement of the range. It will of course be 0, right? So this definitely will go to 0. And so from this other side, what I got finally was that, so if the Peckley of course can cancel out. Right, I found that I had the evolution plus the, so like advection of the cup mixing average. So I have the U average sitting here is 0, right? So the important thing is the equation is unclosed because whereas here I have the cross section average, here I have this what I defined as a cup mixing average, which is the integral of C across the cross section, integral of U and UC across the cross section, right? The velocity profile is also sitting in this. Okay. So if you look back to at the previous lecture or to your notes to see what that Cm is, it's just integral r dr of U into C, not of only C. Okay, so I believe this is where we reached in the last class. Okay, and so now we have to look at the projection onto the range. So this gives us our reduced model. What I now need to do, however, is to close the model by finding this cup mixing average, right, in terms of C bar. But that just means I need to get some approximation for C tilde. Once I do that, I can calculate what is Cm by doing the integral. Right? So Cm is integral U into C plus C tilde. I mean the C bar, C average plus C tilde. Fine, so let's do that. So what I'm going to do is go to my original equation now, but now look at the complement to the range. Sorry, to look at it in the range. To find that, all I need to do is take my equation and subtract out this. Because this is the stuff that's in the range complement. If I remove it, I will get the stuff that is projected onto the range. Okay. At the same time, because I want to get an equation for C tilde, I'll also replace C by its decomposition. Okay, so that's what I'm going to do now. So I'm getting the equation so I start with the original equation and then I just have to subtract this out, okay, at the end. So from there I will have L C tilde, okay, plus L C cross section average, but that of course will go to 0 because that is the null space part. If you want I can do this, but this is of course 0. It's obviously 0 because C is constant and the derivative operator will make it 0. But even without actually seeing the calculation, you know that L is acting on the null space, right? Because this is not just C bar into 1 really. This is just an amplitude. The actual vector is 1. And that is the null space of L. So definitely this will be 0. You see, so automatically you will get always an equation only for C tilde. And this must be equal to, if I come on the other side now, I'll have Peclet times many terms. Right? So the first guy will give me again D if I decompose it. So now I'm decomposing it. Okay, same thing I will do there. Okay, so I just put in my decomposition, and now I need to subtract out this equation. Okay, both the LHS and the RHS. The LHS LC was just 0, right? So I just have to subtract these two terms from this right hand side. So I'll have minus so I can write it like this. Okay, so that is nothing but Cm. Right? The average of U into C is Cm. But I wrote it in the decomposed form. Okay, so now you see something important has happened, right? That if I look at the terms on the right hand side, there are some terms which are independent of R, which are effectively constant. This is one such term. This term will depend on R because C tilde depends on R. This term depends on R because U depends on R. However, U can have its average and fluctuating part. So if I write U as U average plus fluctuating, the U average into this will be constant. Okay, this will definitely again fluctuate. So you see that is exactly the stuff that I can cancel out from here. Right? That was in my range. Right? So this whole term will have some average that will become a constant. This is already constant. These are the things that I'm cancelling out. Right? And why is that important? Because if you look at what I'm doing, I have an equation for C tilde. So I basically have L C tilde equal to right hand side. Now suppose that right hand side, which is a sum of terms, let's imagine the part of the right hand side which is just constant. Then I would be trying to solve L C tilde equal to constant. Right? But what is L again? Remember, is this equation, this operator. Right? So the question is there some C such that taking the derivative of C will give you a constant? So that is not possible, right? Because you know that that lies in the range complement. There's no such function that you put in here which will give you a constant given your boundary conditions. Okay, so that is the whole point of saying that that equation would then be not solvable, right? Because there will be no such C tilde such that when L acts on C tilde, it gives me a constant. That there is a solution. So anyway, I can solve, or in other words, I can get a solution for C tilde only for a special right hand side which has no constant part. But that precisely means you have to put the right hand side in the range of the operator. Right? This is called the solvability condition. Without that, you cannot solve the problem. But that is precisely what our decomposition already did, right? Because you projected the whole equation into the range. That basically involved subtracting out the range complement part, right? So this subtraction is precisely subtracting out the constant part from the full RHS. Of course, because to get the equation here, I in fact took the full RHS and projected it onto the range complement. That means I took its average, right? So that stuff this is a constant because it's the average, right? And that constant part I've multiplied by 1 if you like and subtracted out. Okay, so that ensures that whatever this stuff is, it's going to lie in the range. That means I can calculate a C tilde which gives me this right hand side. That will be the correction. But now you can say, okay, C tilde, this L also has a null space. That means if I find some C tilde here, I can add any null space vector to it, it will still be a solution. Right? Because L acting on the null space will make it 0. So if I find a C tilde which gives me the right hand side, C tilde plus amplitude plus null space vector will also give me the same right hand side. So I have infinity of solutions, generally. But now it has become unique because I have this decomposition condition, right, which requires that the average of C tilde must be 0. That's why the decomposition is important. So I decompose it into null space and things perpendicular to the null space. So automatically I'm looking for a C tilde which has no part of the null space. So that gives me a unique solution, you see. So in general, I cannot solve this problem, both because RHS need not be in the range and because L is a null space. And therefore, I can add any extra null space vector and get infinite solutions. But the way the decomposition works, I fix both problems. I put the RHS into the range, and I have already required that C tilde is perpendicular to the null space, which means that its average in this case must be 0. So this will come in as an extra condition to force me to get a unique solution for C tilde, to eliminate any constant addition I might want to put on top of C tilde. Okay. So now with that in mind, we can directly solve this problem, okay, in principle. However, of course, if you see in general, there are C tilde sitting on the right hand side. So it's linear but not a straightforward solution, right? The right hand side is not something independent of C tilde. I cannot just invert L. So therefore, what I need to do is take a perturbative, that's what I will do, right? Because I'm looking at the problem for small p. So I'll try to get an approximation for C tilde, which is generally what one has to do. Okay. Because the full equation is, this equation is as complicated as the original problem. If I solve this, I could have solved the original problem analytically, okay, which reduces my need to do all this reduced modeling. So always typically at this stage, I'll have to approximate. So first of all, I can already see I can knock these two guys off. Right, and here if I look at it this way, I will see that I have U average plus U fluctuating. I can write this as, right? So U fluctuating into this will be 0. U average into this will come out, right? And that I can subtract from here. So we will see what happens in a second. So let's do a perturbation expansion now. I'm going to approximate C tilde for small p. Okay, so I'll do the standard thing. I look for a Taylor series type expansion of C tilde. Now notice if when I try to do this right in the beginning for C, I had a problem, right? Because C naught I was undetermined, right? It was telling me that it's in the null space. But that's exactly when I realized it's not a simple perturbation problem. So from the pure idea of like algebraic perturbation theory, the Lyapunov-Schmidt reduction has split up the problem in such a way so that you can now set up a regular perturbation problem, which is a normal regular problem, right? Well defined. You somehow regularized the problem by removing out the null space part. So now you can write this nicely. So when I do this and I substitute for C naught, right, I'll get is equal to 0. Okay, because because Peclet is equal to 0. Okay, the leading order term comes when I compare powers. So what I will do is substitute this in here and compare powers of Peclet, right? So L C naught will come here, this is multiplied by Peclet, so there is nothing to contribute, so I'll get this equal to 0. The only solution, of course, is the null space, but I am now going to require that C tilde is orthogonal to the null space, so therefore this implies, right, that C naught tilde must be just 0. Any questions about this? It's exactly the same equation I would get if I had done perturbation here, except here I would now realize, oh, that C naught lies in the null space, right? But here I have solved that problem because I am looking for the deviation variable, which cannot be in the null space, right? And the null space thing, which was undetermined then, is now getting determined by my reduced equation when I project it onto the range complement. Okay, so you see how it is working out. So this K is now 0. So I look for C1 tilde. So this is at order 1, now at order P. So again I have the same linear operator acting on C1 tilde. Okay, is equal to, now I'll have something from the right hand side. What would have been constant is cancelled out here. Okay, and remember all these terms now will have only C tilde naught, because there's already a Peclet sitting there. So for it to be of order Peclet, I have to put the 0th order stuff here. So all the C tildes will go off because they are 0. This term will not contribute, this term will not, this will not contribute, right? So in the end, you see what I have is simply Peclet times, only this term will survive, right? This term and this term. And so the U can come out. The only difference is here I will have U average coming out, because this term is not there. So I see U into this. This U can be written as U average plus U deviation. Right? U average part will come out. U deviation into this will just give me 0 under the average, right? Because average of U deviation is 0. Okay, so what I will get from here finally, if you work it out, is just U minus U average dou by dou x of C. So of course there's no Peclet. So this is clear? So to get this, of course, I use the fact that, which I was saying, right? If I write this as right, that's what this term is, because C tilde goes off, so I'll get this, right? And then I can write this as U, right? And this is 0 by definition, right? So I only have this. That's coming. Okay, fine. So now our task is to find C tilde, which I can do, right? It's basically saying this equation 1 by r, dou by dou r, etc. of C tilde is equal to some right hand side. This right hand side is a function of r, right? With no constant part by construction, right? So all I have to do now is solve this linear boundary value problem. This is a constant amplitude. Right, so the only thing is the r variation here that I need to somehow integrate out. Okay, so let's do that now. Simple exercise. So what I have now to solve for C1 tilde is is equal to U minus U average, right? So what was U? U itself was U average, 2 U average into 1 minus R square, correct? So I'll have this right, I hope you can see that. Yeah. It's just 2 into 1 minus R square minus 1, okay? Because this stuff into U average was U minus U average. And this whole thing is like a constant as far as this equation is concerned. And what will I get here is 2 minus 1, so 1 minus 2 r square. Okay, so if you treat this whole block in front of it as some constant like amplitude, right, is 1 minus 2 r square that you have to deal with. So you can now solve it by direct integration, multiply by r, integrate, divide by r, integrate, and apply the boundary conditions, right? Which is that C1 tilde derivative must be 0 at r equal to 0 and at r equal to 1. And then you also must require that the integral of C1 tilde be 0. That will automatically just tell you that when you write the general solution, you should not add a constant, because If I look at this equation and I say, okay, I can get a particular solution, but I also have the homogeneous solution, right, which is just C1 tilde equal to constant, that I should throw away because my C1 tilde cannot have an average. Right? Average must be 0. That's all it says. So that means I need only consider the particular solution, which we can obtain by just direct integration. Okay, so please do that and tell me what you get for C1 tilde. Okay. So after some algebra, right, you should be able to show that C1 tilde is, right, so this part just comes along like a constant, and then you should get r square by 8 minus r to the power 4 by 4. Sorry, other way around. By 8 minus 1 by 12. Okay, so hopefully you got this. So all you have to do is multiply by r, do an integration plus a constant, right? Divide by r, do another integration, add another constant, and you find the constants by enforcing the no flux, zero derivative Neumann boundary conditions, okay, and you'll get this solution. All right, so now we have C1 tilde. This means I have my first approximation to the center manifold. Right? I know what that deviation part is. And you can see that as we had anticipated, the deviation part depends on the cross-section average. So therefore, this deviation part will vary in x and in time, but only through C bar. Right? Its direct dependence is only on r because it gives you the deviations in the radial direction, right, about the center manifold coordinate, about the cross-section average. So in other words, if I wait for long enough time so that the system collapses onto the slow manifold, right, I'll have the behavior of just the average concentration and the small deviations, which are small because Peclet is small, right? So the deviations are this, which are multiplied by Peclet. So they are small. Those deviations have the following form, right, which has some kind of parabola adjusted to have Neumann zero derivative conditions. Okay. Yes, so now that I have this, I have the full equation for C, right? So therefore C is C average plus Peclet times all of this stuff. So this means I can now calculate Cm. Okay, so what I would get is, so I can now say that the cup mixing average is, sorry, I'll use the definition, right, of the velocity profile u, right, which you know is 2 into u average 1 minus r square, into this stuff, right, C average. So that will, this with the, this C average will just give me a C average outside. Of course, I have to put this also. So if I write this as u average plus u tilde, u average into this, and this will just give me the first contribution of Cm is just the C average itself. Plus there will be an order Peclet correction, C1 tilde, and then higher order terms, which I have truncated. So here you will get Peclet into all of this stuff. The u average will cancel out with the denominator. Okay, so only this r variation will give me a correction. That's how the cup mixing deviates from the cross-section average, precisely because the concentration field has order Peclet deviations. So I'll not do the algebra now, but just tell you that you will find, so the deviation of course looks like that. Right? There will be a u also sitting there from here. Okay, the u average from here will get knocked off by that, and so this is all constant, and there's a 1 by 48. Okay. So this stuff, this variation, right, gives you a 1 by 48. Okay, this in turn has come, remember, from the nature of the velocity profile, from u tilde. Okay, so that's the important thing to remember. This U tilde sets the variation of concentration about the mean, which in turn sets this value. Okay. Already, if you are familiar with Taylor-Aris dispersion, you recognize this 1 by 48 is the term that comes in the Taylor dispersion coefficient. So if I change my channel, if I get a rectangular channel or a flow between two flat plates, which I showed in the simulation, this velocity profile will change. Okay, and that will change this, and ultimately you'll get a different constant in front of the Taylor dispersion coefficient. Okay, we'll see that in a second. So that's where this 48 number is coming from. It has to do with the velocity profile. Okay, in particular, the velocity profile is a plug, right? So if I just have a flat velocity like a plug flow reactor, right? So a plug velocity, this is going to be 0 because the velocity is just U average. That means this will be 1, 1 minus 1, you will have 0. Therefore, there will have 0 here and there will be no correction. This will become 0. So the entire concentration is just the cross-section average. In which case, there will be no correction to the cross-section equation. Cm is equal to C cross-section and your reduced equation is directly closed. You will have ddt of cross-section average plus U d by dx of cross-section average equal to 0. Just advection and diffusion, no dispersion. So dispersion is coming entirely because of the deviation from a flat velocity profile, and the extent and nature of that deviation will give you the dispersion coefficient value. Okay, fine. So now I have this, so I can substitute in my reduced model, and when you do that, right, right, so I'm going to write it in this way. So I get the C bar into dou C by dou x, right? And then I have the Cm stuff, okay, which I'll take to the other side. Sorry, there's a minus sign here. I take this to the other side. So U square comes because remember I have U d by dx of Cm, right? Cross section average of U d by dx of Cm. So that U and that U gives me a U square. Okay. And remember I have this derivative which will act on this derivative. So I get second derivative. Okay, so this is my final reduced model. And remarkably, this is what we were trying to look for right from the beginning, right, based on our simulation videos. We see that at long time, the reduced effective model has the time evolution being given by usual advection with the average velocity. So this is like the advective transport in a plug flow reactor, where there is no velocity profile variation. The velocity profile variation induces this new term, right? And this is the diffusive term in the x direction. Right? That's what gives rise to this Gaussian kind of spreading, right? And this is precisely what's called Taylor-Aris dispersion. Okay, and the Taylor-Aris dispersion coefficient, right, is this. Right, so you have a dependence on the average velocity squared. Should be careful. Right, average velocity squared by 48. This 48 number is coming from the kind of velocity profile, right? It will change with different velocity profiles, but the U square will not change. As you can see in the calculation, this U square will always be there regardless of whatever function of R you put here. So if I replace this by function of R, which is just U tilde, U deviation, right? Different function of R or different function of Y depending on, so if it was in flow between two channels, this operator will change, this function will change. So the final solution will change. The functional dependence on the transverse direction will change, but the fact that there will be a U here will not change. Right? So in the end, in terms of scaling, of course it should be like that. You will have U square by 48 times Peclet, small Peclet. Okay. But what was small Peclet? Can you tell me in your notes? So it was, right, UC R square L by D. Right? Right, and then we know Peclet is So this means that the Taylor dispersion is inversely proportional to your molecular diffusivity. Yeah. Ah, correct. Yes, thank you. Okay, so the interesting result which Taylor had derived, right, which is also one interesting thing is advection with radially varying concentration profile produces diffusion in the axial direction. The second thing is that the strength of that diffusion is inversely proportional to the molecular diffusivity. Okay, so in fact, the stronger you diffuse molecularly, the more the Brownian motion, the less will be the emergent diffusion in the axial direction. Okay, so why is that? Because the molecular diffusion causes mixing across the streamlines, right? And in fact, that is what makes small p small. Now we can see in a calculation that if small p were truly very, very small, this correction C1 tilde would be very, very small, which means this term will be very, very small. So that dispersion will be very weak, right? So the concentration looks more and more like a flat profile, right, as the radial diffusion is faster, which means as molecular diffusion is faster. The weaker the molecular diffusivity, the more you'll have variations of concentration, the stronger will be the dispersion effect. Okay, so in fact, tracer-like particles which diffuse very, very slowly, almost follow the streamlines, they will show the maximum axial spreading, right? Because the particles near the center line will move with the max velocity, those near the wall will stay at the wall. That will give you the maximum axial spreading, which will still look like this at sufficiently long times. But remember I said how long or how distant you have to be, that also depends on the molecular diffusivity. Okay, so if you have very small molecular diffusivities, you'll have strong dispersion, but you will see this Taylor-Aris type of behavior also very far downstream. Okay, so there are these combination of things, but assuming that you have a very, very long pipe and you're interested in things at infinitely large distances, you will recover this kind of diffusive spreading behavior with this coefficient. Okay, so what's very interesting, again, so let us now, we have taken this detour from our stochastic processes just to see how this technique of reduced modeling works, right? And the reason is that we will have to use this method to look at the white noise limit of stochastic processes. Right now, it seems like we've gone into a different world, but immediately the two will snap together when you recognize and recall, right, that any SDE has a corresponding Fokker-Planck equation. Right? And the Fokker-Planck equation is just a diffusion-like equation in probability space. Okay, so what we will do in the next class when we try to apply these techniques is we will say, okay, I'm starting with some kind of ODE which has a fluctuating term. Okay, that means there's an ODE which has a right-hand side, fluctuating right-hand side, let's say F. Now I can always say that this F is following some SD, right, which in turn has white noise, but F is not white. F is correlated, random, given by some SD, okay, but not white in time. And I want to know what happens as F approaches the white noise limit, which I can appropriately tune in some way. The moment I say F is itself given by an SD, I can introduce a Fokker-Planck equation. Right? So I can transform from this ODE SD system to a Fokker-Planck equation in multi-dimensions. When I do that, immediately this will become relevant. Because remember, what did I do? I started with a advection diffusion equation. Right? I start with an advection diffusion equation. If you think of Fokker-Planck, it's like I have diffusion in R, right, and some drift process in X. Something similar we will see when we transform the SD problem to the Fokker-Planck space. I'll have rapid diffusion in some direction, right, which is going to give me this rapid forcing. And in the slow direction, which is modeled by the ODE, I'll just have drift. So if you think of it that way for a second, I have the X dimension of some space where I only have drift terms. And in the R dimension where things are happening fast and fluctuating, I have diffusion. Okay. Of course, in the Fokker-Planck equation, the diffusivity coefficient comes in different places, which will make an important difference. But if you think of it at taking a step back, you can see it has that structure. And what happened now, I was able to get rid of the R direction where things are happening fast by using this Lyapunov-Schmidt or center manifold reduction and get an effective equation where there's no longer any R direction. That means I removed it out. I get an equation only in the X direction, right? And that equation now remarkably has a drift term, right? But it also has a kind of diffusion term. But an effective diffusion now in the x direction, which earlier didn't have any diffusion, right? So I took a problem which has diffusion in R, advection in x, I reduced it and got an equation which has advection in x and diffusion in x. And if you think about diffusion as white noise forced Brownian motion, what has happened is I started an equation where I had Brownian motion in R and drift, deterministic drift in x, right? And I got a final equation which has deterministic drift in x and Brownian motion in x. But the Brownian motion coefficient is different. It's not the true underlying physical Brownian motion, it's some kind of effective Brownian motion that is coming out of a combination of drift and noise. So if you think of it this way, if I rewrite this final equation as an SDE system, this would get modeled by white noise. So you see, I started from a problem which has no Brownian white noise motion in the x direction and actually got that. So it's like saying I modeled the rapid fluctuations in R which were affecting x. I could get rid of R completely and model the effect of diffusion in R as a kind of stochastic Brownian motion in x itself. But I need to find the effective coefficient. Right? That's the same problem we are thinking of actually. Right? I have a general ODE system with some fluctuating terms in turn driven by an SD. That is what I have to start with. Right? If I make that hypothesis, if I formulate the problem this way, then I can get rid of the rapidly fluctuating SDs and directly get an equation only for the slow variable. But instead of being an ODE, it will now be an SD with some effective white noise. This is what I want to find out. And what will be this term and how one should interpret it? Is it Stratonovich? Is it Ito? Okay. So we'll look at this properly from the next class onwards. But just now I want you to, before leaving here, see what is the possible connection. Okay. So the mathematical technique will be the same. Because again, I will somehow take my SDE ODE system to a high dimensional Fokker-Planck, and there I will try to get rid of the fast directions of that probability space and get an effective equation only in the slowly evolving variables. And if I can do that, I can go back to SDE type, and that's how I can get this limit. The limit here is Peclet going to 0, infinite, the fast radial diffusion. The limit there will be white noise, which is again, what this means that the fluctuating variables are fluctuating infinitely fast compared to the slow variables. Okay, so this was the connection. We'll see it work out from the next class onwards. Right now, again, just sticking here, the one leftover thing we need to do is look at the adjoint. Right? So let's do that now. Okay, any questions about this? Okay, so what I want to do now is look at this technical point, right? How do you figure out that? I'll just erase it from here. How do you in general calculate the adjoint of this kind of differential operator? We will again need to repeat this calculation when we do the reduction of the Fokker-Planck equation, and there we will see that it is not self-adjoint. That in fact therefore will play an important role. So let's try to do it here. Okay. So the idea is, you just to find the adjoint, you need to use the definition of the adjoint. Right? So recall, I'm in functional space, so the inner product is an integral, right, with respect to the appropriate weight. So here I would say let's start from here. Okay. Start from the LHS, try to bring it there. So what is this? Is integral RdR of, so L is acting on some function u of R, right? So I'll have right times V of R. Okay, so I'll not put the bracket there. Okay, but so V is a function of R, U is a function of R. This is what it means. LU is this, projected on V means multiplied by V and take the appropriate integral. Right? The weight function R here is put because the inner product in this cylindrical coordinate space has the R. Okay. And now what I want to do is try to move the operator somehow onto V and see how it changes form. So that just means that I need to shift the derivatives onto V under the integral. So what should I do? Integration by parts. We've already done this in earlier derivations, right? And remember in the Fokker-Planck derivation, I had to do the same shift. So let's do that same shift now. So if you want, you can remove these guys and later reintroduce them. Okay, or you could have kept them, doesn't matter. So I do first, right, into integral of second, right, to this whole thing. Right, so I write first into integral of second, so because I want to get rid of the derivatives, right. Right, so I get this. Yeah, I give my 2 everywhere. And this stuff in turn is equal to, again I can repeat the same exercise, right. So now I take this as the first, this as the second. Minus and minus plus differential of the first, right? So okay. So I get this, and now I can multiply and divide by r dr again. And I recognize that this stuff is basically right. And the operator hasn't changed form. Right, so if you want, you say this is L star V, and so L is equal to L star, of course. So I have 1 by dou r of V now, right, into U and the inner product. Okay, so I did it, and then I multiplied and divided by R again to get the final form. So this is true without any extra terms, provided these boundary terms go to 0. Right? Otherwise, I would have to say Lu comma V inner product is U comma L star V plus some extra stuff, right, which are the terms on the boundary. But what happens to those terms? Right, with my boundary conditions, they knock off because I have dou by dou r of the stuff equal to 0. Right? So the operator is defined not just by its differential expression, right, but also by the boundary conditions. So if I apply the boundary conditions on U and V, both these guys will get knocked off. Okay, so the same differential expression, if you like, with different boundary conditions can become not self-adjoint. Okay. That means the expression will stay the same, but the boundary condition would be different for the L star. But in this case, with no flux, I do have a self-adjoint operator. L is equal to L star. The boundary conditions also same. How do I know that? Because the question is what boundary condition I need to apply on V. Okay. So here on U I applied derivative is 0, that knocks this off. Here I put derivative 0 on V, knocks this off. Okay, so you can see by this sort of calculation, I can sort of infer, right, that indeed this is true with L star equal to L. In that way, it is self-adjoint. And this always happens for this kind of diffusion operator with Neumann boundary conditions or periodic boundary conditions also. Okay, because you see, if it was periodic, I would say this function at left boundary and right boundary. Again, they would cancel out because it's periodic. Right, so in the Fokker-Planck equation, I can look at the Fokker-Planck equation with no flux boundaries or with periodic boundaries or going to 0 far away. All those boundaries would knock off and remain self-adjoint. Right, the important thing is, here I have a constant diffusion coefficient. In the Fokker-Planck equation, the diffusion coefficient is not constant. Suppose there was a diffusion coefficient here which was a function of R. Then when I do this integration by parts, you see the diffusion coefficient will go inside, and then the two will not be same. Right? It's only when the diffusion coefficient is constant, it can take it back out. Okay. So equation with constant diffusion coefficient, the diffusion operator is self-adjoint. When it is not constant, it has to come in a particular way, which is not true of the Fokker-Planck equation, right? Because it's not actual physical diffusion equation, right? It's the probability space equation. The D doesn't sit inside the. So when you have diffusion a function of R in normal physical diffusion, you will have D sitting here, right? And that is self-adjoint. But the Fokker-Planck equation, the D sits here, at least for the Ito Fokker-Planck equation. So anyway, we'll come back to that in the next class. But you can see at least now here, this is how one works out whether it's self-adjoint or works out the adjoint. You can see that here it is indeed self-adjoint. So therefore, the kernel of L is same as the kernel of L star, which means the vector 1 spans not only the kernel of L, but also the range complement of L. That's what we have used in our derivation. Any questions about this? Okay, so now before ending this lecture, I want you to look at the following slide. So throughout this last, let's say 3 classes, right, we have gotten into the world of slow manifold reduction, and this has required us to understand a few things, right? You need to have some idea of dynamical systems theory, fixed points and linearization about fixed points, and the relevance of zero eigenvalues or a null space. Okay, that's one aspect. That's the non-dynamical systems part of it. That is reasonably, I think, familiar to most people. But then when you apply this ideas to PDEs, you need to know quite a bit about linear operator theory to find the null space and find its adjoint and the kind of things we are doing here, right? Which are like elementary aspects of linear operator theory. So if you want to get more into this, I taught you what you need to know for our lecture, right? Which is to look at the white noise limit. So now that you've at least understood, at least in terms of applying the technique, right, to these problems, which I showed you in the last 2 classes, we can now go forward, apply it to our stochastic processes. But if you want to understand things more deeply, right, to get into this world of order reduction more generally, right, then there are some basic books you can start with. So the best introduction to understand what's going on in slow manifold reduction, and also the most general kind of method to attack problems with this technique, especially using computer algebra, is in this very nice book by Anthony Roberts, okay, which is shown here. It's a SciAm publication in 2015. So that would be the ideal one place to look at, right, which he covers all kinds of techniques in a unified way. But again, it requires some amount of work. Right? What I have shown here is directly the Lyapunov-Schmidt reduction, which also Gardner uses. Okay? And that technique has been applied extensively to problems in chemical reaction engineering, in transport in reactors, dispersion in pipes, and so on, by Vemuri Balakotaya, professor at Houston, and his collaborators. Okay, so there's a sequence of papers starting from the late 90s, early 2000s, right, looking at all kinds of different systems. Where essentially what I did in this lecture on Taylor-Aris dispersion can be done under steady state, but where you have, for example, a reaction. It's under steady state, d by dt will go to 0. Okay? But you can introduce, for example, a reaction, and the presence of the reaction will mean that the concentration will evolve along the x direction as the material is consumed. And you may want to find a reduced equation directly for how the cross-section average decays along a reactor, right? Because of a reaction. Right? This is classic plug flow reactor kind of design problem. But typically you know that the velocity is not truly plug. That's to model that you add dispersion. Right? So plug flow reactor with Taylor-Aris dispersion is a kind of effective model used in reactor theory. So where does that dispersion coefficient come from? How will you adjust it if the velocity profile changes? Is the dispersion affected by the reaction itself? Right? The answer is yes, because from what you have seen here, the dispersion coefficient 1 by 48 and so on has to do with the concentration profile. Now if I introduce a reaction at the wall or in the bulk, right, that will of course change the concentration profile. So indeed the Taylor-Aris dispersion coefficient is different with and without reaction. Right? In reactor theory, this will be recognized by saying I'm doing experiments under cold flow to get a dispersion coefficient. When I then use it in a hot flow experiment, that means you have the reaction, the results need not match. Right? You have to do the experiment under hot flow. So this kind of technique can give you an exact analytical result, at least under simplified conditions, and give you an insight into how the reaction of different types and different orders can affect the dispersion coefficient. Things like this. Okay, so there's extensive work by Professor Balakota and his collaborators. So you can go to your favorite search engine and type in his name and look for his papers. Okay, and usually most of his papers have an introductory treatment of the Lyapunov-Schmidt. He also has a couple of review articles, I think. And then, of course, to understand this in detail, you need to know basics of linear operator theory. Okay, so here are some books. So this first one is a book by Jotso and Wolensky. Okay, it's a nice, reasonably gentle introduction to both matrix algebra and functional analysis and linear operator theory. Okay, with nice examples and a lot of verbal discussion. So it's a good way to get into the area and to start thinking abstractly. Then Balakota himself has a book along with Ratnakar, which was published recently, second edition last year. Both these books are in the library. Okay, so I myself have yet to read Balakota's book, but given his extensive work, I think it would be nice to look at. Okay, so here are two books, both are in our library, okay, in the IIT Bombay's library. And then there are, of course, two classic texts. Okay, so there's the book by Naylor and Sell on linear operator theory. It's more advanced. Okay, so if you directly go to that, you may struggle. It may help to look at Jotso's book, for example. And then in chemical engineering, there's a classic text by Ramakrishnan Amundsen, linear operator theory in chemical engineering. Okay. This book, unfortunately, is out of print, but it's an excellent classic text. So if you can get a hold of some version of it, it will be nice. Of course, again, it's at a slightly advanced level. So it may help to look at Jotso and Wolensky first. But I personally prefer this book by Ramakrishnan Amundsen. Okay, so here are some resources, right, if you want to get more into this. But for our course, the main purpose of introducing this method was to see how we can get the white noise limit, right, and see whether it is Stratonovich or not. So that we don't need to go deeper down this path. We will return in the next class to stochastic processes and see how we can apply this reduced order reduction technique to answer that question. Is Stratonovich really the limit of white noise? Right? When you start with a correlated process forcing a dynamical system, you take that correlated process to white noise limit, make it delta correlated. Is the equivalent SD Stratonovich or not? And how can I derive it? How can I derive the strength of that white noise forcing? Okay. This is what we'll do in the next class.